Hello and welcome to G Fun Facts Online. What if I told you that scientists are building time machines? Not the kind from sci-fi movies, but giant telescopes that let us look back to the very beginning of everything. Today, we're going on a journey over 13 billion years into the past, to a time before the first star ever twinkled. Imagine a universe fresh from the Big Bang, not filled with sparkling galaxies, but with a thick, opaque fog of hydrogen gas. Astronomers call this the cosmic dark ages. It was a period of absolute blackness, but that darkness wasn't going to last. Sometime between 50 million and a billion years after the universe was born, the first stars ignited. Their intense radiation started burning away that primordial fog, like a celestial sunrise, in an event we call the cosmic dawn. This process, the epoch of reionization, made the universe transparent, allowing light to travel freely and creating the cosmos we know today. But how on earth can we see this happen? The light from that era is impossibly faint, stretched and weakened by its journey across an expanding universe. It's like trying to spot a single firefly from a million miles away. Yet, we are doing it. This is the story of the incredible technology that is unveiling the universe's first light. So how do you see an event that happened before light could really travel? Well, one of the most direct ways is not to look for the first stars themselves, but for the effect they had on that giant ocean of hydrogen gas. You see, neutral hydrogen atoms can do something pretty special. The single electron can flip its spin, and when it does, it emits a tiny pulse of energy, a radio wave with a precise wavelength of 21 centimeters. Now, for one atom, this is a super rare event. But there was so much hydrogen in the early universe that this 21-centimeter signal was everywhere, a constant, faint hum filling the entire cosmos. As the universe expanded over 13 billion years, that signal got stretched out, or redshifted, to much longer wavelengths, around 1.5 to 3 meters. So if we can tune our radio telescopes to asterisk that times frequency, we can create a 3D map of the hydrogen gas, and literally watch as the first stars carve out bubbles of transparency in the cosmic fog. The problem is, this ancient whisper is buried under a deafening roar of cosmic noise. Our own Milky Way galaxy and countless other radio sources are screaming in the same frequencies, thousands of times louder than the signal we're looking for. It's a monumental challenge, and it requires a new generation of super powerful radio telescopes. A global effort is underway to build a radio telescope armada. The flagship of this fleet is the Square Kilometre Array, or SKA. Currently being built in the remote deserts of Australia and South Africa, the SKA will be the world's largest radio telescope. Its low-frequency antennas in Australia are specifically designed to finally capture the cosmic dawn in stunning detail, moving beyond just detecting it to creating detailed 3D movies of how reionization unfolded. Paving the way for the SKA are several Pathfinder telescopes already scanning the skies, like LOFAR in Europe, the Murchison Wide Field Array in Australia, and the Hera Array in South Africa. These are our scouts, developing the techniques needed to filter out all that noise. And this search has already had its share of drama. In 2018, a small experiment called EDGES in the Australian outback reported a stunning detection. They claimed to have found the 21 cm signal from just 180 million years after the Big Bang. But the signal was twice as strong as any theory predicted, hinting at new physics or even the influence of dark matter. It was a tantalizing clue, but the result has been controversial. Other experiments, like India's CERES-3, have been unable to confirm it, suggesting it might have been an error. This ongoing scientific detective story just shows how incredibly difficult this search is. While radio telescopes are listening for the gas, other observatories are trying to see the culprits directly, the very first stars and galaxies. To do this, we need to look in the infrared. The fierce ultraviolet light from these first stars has been so stretched by cosmic expansion that by the time it reaches us, it's been redshifted all the way into the infrared spectrum. And this is the specialty of the one and only James Webb Space Telescope. JWST was literally built for this purpose. It's nicknamed the first light machine. With its massive golden mirror, it can see further back in time than any instrument before it, and it's already delivered spectacular results. In a patch of sky that looked like a faint smudge to Hubble, JWST found 717 young galaxies, all existing within the first 650 million years of the universe's life. These primordial galaxies were more numerous and more structured than anyone predicted, giving us vital clues about how the universe got lit up so quickly. But there's a third, incredibly clever way to probe this era. It involves looking at the oldest light in the universe, the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang itself. As this ancient light traveled across the cosmos, it passed through the gas that was being zapped by the first stars. The newly freed electrons scattered some of that CMB light, leaving a tiny, subtle fingerprint on its polarization. By measuring that fingerprint, we can figure out exactly when reionization happened. For years, only space telescopes like WMAP and Planck could make this measurement. But recently, in a groundbreaking achievement, a ground-based observatory called CLASS, perched high in the Atacama Desert, made the first-ever detection of this signal from Earth. Battling atmospheric noise a million times stronger than the signal itself, CLASS proved it could be done from the ground, opening a whole new window for studying the cosmic dawn. So we have this amazing, multi-pronged attack on one of the biggest questions in science. Radio arrays like the SKA are mapping the fog. Space telescopes like JWST are spotting the lighthouses. And CMB experiments like CLASS are checking the timeline. Together, these incredible instruments are taking us to the very edge of time itself. We are truly living in a golden age of cosmology, on the verge of witnessing how our universe emerged from darkness and became the brilliant, light-filled cosmos we see today. The dawn is coming.